So I'll first start by giving a slightly bigger picture on fair division problems and mention some basic variants. So in these types of problems, we have a set of agents. I will always use n to denote the number of agents, and then will be a set of items, m, and these will be, for today, always indivisible. So indivisible items, we can only give each item to one person. And then each of the agents have valuation functions which for every subset of the items assigns a value, how precious it is for this particular agent. So VI here refers to the agent. Some basic properties we will always maintain is that empty set is worth nothing. These valuations are monotone, getting more won't harm you, and they are sub-additive, that like the sum of valuations on two sets is at least the value on the union. And so the general goal, as if we see it as an optimization problem, is to find a partition of the items that maximizes the welfare function. And the question is what this welfare function is. So let me give you three basic examples. So the first one, which the economists just usually call the social welfare, is simply to maximize the sum of VISI. So we just add up all the utilities these agents derive. And so, you know, there are a number of issues with this. If we try to look at it from like a fair division perspective, it really kind of means that giving $1 more million to Jeff Bezos has the same societal effect than giving $1,000 to 1,000 starving children in a refugee camp. So it's in that respect, it's a questionable objective. And in fact, if you really want to go for equality, and so then we can look at, actually focus on these refugee children and want to maximize what the minimum any agent, any member of the society gets. This is called the Santa Claus problem, and it is to maximize the minimum over VISI. This is kind of really more like the fairness children see it. They really are eager not to get less than anyone else and don't necessarily care about something like global maximizing the overall sum. So this is kind of more radical in like ensuring that everyone gets at least something, but the kind of problems are that, well, we really don't care what happens above that. We don't care whether like everyone is just a notch between the above the absolute poverty line, or if there is a distribution of also more wealthy in this group. So that's where the Nash social welfare comes into play, which is what I will mainly focus on today, is to maximize the geometric mean of these valuations. So I'll always do this normalization, which will be important if we want to think of approximations and so on. So I don't simply look at the product, but the actual geometric mean. And so this says, like, in contrast to social welfare, where some agents can get nothing, like the Santa Claus, of course, like ensures, if at all possible, to give something to all agents. That's also true for Nash social welfare, but it's kind of a more smooth trade-off between.
Sorry, question about the model. So there is a centralized power which distributes the.
Yes. So we, well, there are many variants, and probably the more interesting and realistic are also in mechanism design. We are really just looking at it as an optimization problem. But it's kind of a smooth trade-off between these two extremes. You can make a compromise of giving a little less to the less well-off if it can be compensated by huge benefits for many people. So the reason this is called the Nash social welfare, it is kind of motivated by or related to Nash bargaining, or can be seen as a special case if you look at the space of all possible allocations. And another kind of nice property, it's invariant under scaling, which means that if we replace all valuation functions by a constant multiple, it doesn't affect the optimal solution, whereas for the others, if someone over or under reports their valuations by a factor of 5, they might massively benefit from doing so. So it's kind of a nice robustness property here. Now, so these are the main objectives, and now I'll talk about valuation functions. So the first and most natural example is additive, where the value on a set is sum of Vij's for j in the set for some non-negative Vij values. There is, so that because Thomas just came in the room, I define a special case, the restricted assignment, where these valuations are kind of sort of the same for everyone who cares about this object, which is Vij is either 0 or Tj for every agent for some fixed values Tj. And then, so this was a special case, but otherwise I'm going upwards to more general classes. So there are gross substitutes or M natural concave valuation. So this is something you heard from Yannick about in Yannick's talk. I won't define it, but that mentions some important properties. So this is actually a very nice subclass of submodular, which is in turn a subclass of subadditive. And just looking at the hard mass results, so this is like the most specialized class. Let's just so for social welfare, how do we compute this? Sorry?
Greedy?
Yeah, I think greedy is also kind of an overkill for a term for the algorithm. We simply take every item, look at the Vij's and give it to the person whose Vij is the largest. So that's good, but if we look at the other two Santa Claus or Nash social welfare. This is MP complete, and this goes back to the subset sum problem.
So it's a restricted additive.
Restricted. So what's the right?
Just below.
Restricted assignment. Yes.
Just below. Okay. Do you mean restricted assignment below or just additive?
So restricted assignment is a special case of additive, but even yes. So even the additive works the same way for social welfare. Yes. Sorry. So I actually wanted to start with restricted assignment because for these two valuations, this is MP complete, because if I look at these numbers T1 to Tm integers, and I'm interested in whether there exists a partition of these m numbers such that the numbers in A equal the numbers in B. This is exactly, if it has solution where these two are equal, if I get the best possible Santa Claus or Nash social welfare objective for just two people, where everyone has the same valuations, both of them. Okay, so now I'm gonna draw a big table here and just write some results regarding these different objectives. So I write here the sum of Vi as I, the minimum of Vi as I, and then the geometric mean. And here I start with the restricted assignment, additive. Here I leave a gap because I need that row later on. I write gross substitute, submodular, and subadditive. Let's get a nice orange grid here. So these we have seen actually already for additive. It's polynomially solvable. The nice class in this context is gross substitutes. This can also be solved in polynomial time. It's Kuhl and Staccati result from 99. In fact, it turns out that this cross substitutes, which I still haven't defined and will not, is exactly the class where this is solvable in polynomial time. If you give me a class of valuations under mild assumptions where, however you pick them, you can compute the corresponding. Yes, maximizing this objective would correspond to a certain Woolridge and market equilibrium concept, and then these cross substitutes are exactly done, and you can do that. So for submodular, that's MP hard, and there is an E over 1 minus E by von Drach from 2008, and this is optimal. Like, you can get such an approximation and shows that nothing better can be done there. And then there is for subadditive a factor 2 by Végh from 2006. So, except for mystery line, this is what we know about the standard social welfare, the sum of the valuation. So for restricted additive, there are for the min max or the Santa Claus objective, There is, I think that the current best is 4 plus epsilon from Sunny Davis, Thomas Rothfuss, and Zhang from 2020. There has been lots of work on both additive and restrictive additive, and this additive is really a stubborn open question to this day whether there exists a constant factor approximation. The best ones here, there is like a square root n log cube n by Asadpour and Saberi from 2007. So n is the number of agents, and then one can also do m to the epsilon. So m is the number of items, which is at least the number of agents for the problem to make sense. So in that sense, the m results are weaker. One can do m to the epsilon in time, or m to the order 1 over epsilon, which means like one can do polylog approximation in quasi-polynomial time. So this is by Chakrabarty, Chusoy, and Khanna from 2009. And again, as I said, this is really a stubborn open question. I don't think people would even venture much further here, did they? Like for more general valuations.
Well, people definitely tried the additive is more.
Yeah.
Wasted a year on it, but yeah, it's a
So we have the Thomas stamp on hardness.
One implication of what I talked about on Tuesday is that you can go for cross substitutes. You can get a constant factor approximation if you are allowed to assign each item a constant number of times.
If you interesting. So here for the min max, if you are allowed to oversell multiple copies, then you can get the original.
The original object, yeah, the original original. So it's resource augmented.
Okay, and who is that by? Who is that by?
That's just an immediate implication of what I talked about on.
Okay, perfect. Thanks. So, let's now move on to Nash social welfare. Now here people haven't quite looked at restricted additive. There is an even more special case when all agents have the same valuations and one can do a p-test. But already for additive, this is APX hard, this problem. So I'll start with this and mention some results here. So NSW, Nash social welfare with additive valuations. Before the results, let me start with the simple basic relaxation. So if I pretend that I can divide my items and xij is the amount of good I assigned to agent j, then this will be sum of Vij xij is the value of for agent I, and my resource constraints are that sum of xij is at most 1 for any good and x is non-negative. So for a 0-1 solution, we really get an assignment that this is a convex relaxation. In fact, so noting that if you take the log of the objective, this is maximize sum of log sum of Uij xij, and those of you who have seen some like market equilibrium computation papers talks might realize that this is the Eisenberg-Gale convex program from '95, whose optimal solutions give the market equilibrium for divisible goods and linear utilities. So if you stare at it and look at like the optimal Lagrange multipliers, they will beautifully correspond to prices here, and this assignment and prices will be such that everyone spends $1 on a market on buying their best preferred bundle at these prices, and all goods are exactly that the 1 unit is sold, and so this is like what has been very well studied in like classical mathematical economics. But if we look at, so this is just a good correspondence to keep in mind. Unfortunately, if you look at this market relaxation, it doesn't work very well. It has unbounded gap. So what is kind of a good test case for fair division problems? What if I have n agents, like 4, and I have 4 items, one of which is like something very precious, a diamond crown. Everyone really would like to get this, and then the others are just some little glass beads, which everyone has utility 1 for. So let us define Vij is m if j is 1, and 1 if j is greater than 1, and this m is very big. So what is the optimal social welfare? If we cannot just chop out this crown, then we will give it to one person, and then all the other n-1 people get 1, so that's 1 to the n-1 to the 1 over n. So this is m to the 1 over n is the integer opt. And then, well, what's the fractional optimum? That's I can equally spread out all the goods to everyone, so everyone gets the total value m plus n-1 over n. And now I don't need to take like this to the n 1 over n through, so this is the actual fractional optimum. I equally shared all the resources, and as you can see, this gap between m to the 1 over n and m over n is pretty unbounded. So what can we do about this? And so this is actually very fascinating. There has been like 3 basic approaches over the last 6 years. So the first was by Cole and Gatsalis in 2015, who gave a 2.89 approximation. And the starting point was this connection to markets, but they realized that, okay, now in this market equilibrium, this crown is a money sink, somehow all the money is going there, so they defined a variant of the market, which is a restricted spending market equilibrium, and which in a sense one can convert that, which was done in a later paper, to a stronger convex relaxation using different variables, and then they round out the fractional market solution. And so what I kind of found fascinating about this problem, and why I got interested, that the 3 approaches I mentioned are all really different from each other, and each of them is like very, very nice, very clever, elegant, new techniques and insights, which I think all 3 are quite remarkable. Which and what if you see all these things happening on a single problem, then you want to learn more from that problem. So the second, and maybe it would be better to just talk about these basic approaches as opposed to our new algorithm on Rado Valuations, but I actually selfishly go to that and leave these here as kind of just teasers, and hope that you will look at some of them. So the other one, which I'm sure will turn some heads is by Anari, Ovesgaran, Saberi, and Singh from 2017, who gave an E approximation, and this is using real stable polynomials. So what they here basically come up with is a very different kind of relaxation, which is like a max-min function whose convexity follows by like showing that it corresponds to a real stable polynomial, and as the same theory helps to efficiently round this this relaxation to integers. So that's I think a very fascinating application, which shows that like these real stable polynomials are a very powerful technology. And then there is one, the third approach, which is in terms of approximation factors, the winning approach up to now, Barman, Krishnamurti, and Vaishh from 1918. So this gives an E to the 1 over E plus epsilon, which is like 1.45. And this is using the MV free up to 1 good property. So it actually uses some characterizations for fair divisions. It's like a MV free up to 1 good means that like even if Neil gets the crown and I just get this one thing, I don't envy him, because if I remove the most precious item from his bundle, then that's not more than what I have. This is a property of optimal Nash social welfare as well as Pareto optimality, and what they showed that basically if you guarantee these two properties, that will give you an approximate Nash social welfare. So these are somehow equivalent, and getting that is kind of like an alternating path algorithm based on this matching formulation. So these are, again, I do recommend basically looking at all these three papers, very, very insightful ones. And so there has been, so let me just write here the winning constant for now, and those are all the results. And so there have been some extensions of this to like separable piecewise linear concave and some other, like I would say, mild extensions of additive valuations, but somehow they like that the other fascinating property that however you try to extend any of these three approaches, somehow they are all inherently about additive valuations. If you try to venture further, like want to do something other, then it all breaks down. So what we were trying to get a foothold of, we wanted to go towards these gross substitutes, which it's very encouraging that that's like the very rich, well-structured class where we can solve the social welfare in polynomial time, and so we looked at Rado Valuations, which is like a rich subclass of gross substitutes. So I'm now gonna tell you what these are, and so let me raise this board.
Is there anything better for respect to assignment?
I'm not aware, like somehow people think I haven't looked at just quite that. Like if you go even further where all agents have the same valuations, then there is a p-test. But yeah, it might be there, like a little window of getting a better function. I think that's might be already APX hard, so there could be a better constant. So, Rado Valuations. So, in this Nash social welfare, we have agents and goods, and we are basically looking at an assignment in the graph between them. In Rado Valuations, now I'm just looking at a fixed agent I. And each of these agents has a private other bipartite graph. So this is the set of items G, and each of them has a private set Ti, and then edges between them. So we have G, Ti, EI bipartite graph. And they also have a matroid living on this set Ti. And the value of a set S is that and I have weights, which are non-negative weights on these edges. And so the value of a set will be the maximum weight of an independent matching with endpoints in this set. So independent matching meaning that the endpoints on the other side are independent in the matroid over there. So let me write it. Maximum of the Wi Fi such that Fi is matching between a subset X of S and a subset Y in the independent sets. So is the definition clear? So let me just give two very well studied examples. So the first is assignment valuations. Then MI is the free matroid. So I basically just really looking at any maximum weight matching with endpoints in this set period. So this has been very well studied in all this mechanism design context. The other is the weighted matroid rank function. So that you can see in this model by just looking at two copies of the goods matching the same copies by a perfect matching, and then like a maximum weight of a matching inside a set will be the maximum weight of an independent set in this matrix. So these are and what basically these Rado valuations do, they are kind of give you all possible combinations of these sorts of valuations. So these Rado valuations are a subset of gross substitutes, and so how big subset these are? So this actually, when we started looking at this, so the way it evolved, we wanted to solve assignment valuations, and then we got more bullish when we saw that the arguments are quite robust, and threw a matrix on top, but then realized that that actually it's even not clear. Are these, well, that there is an issue that these Rado valuations are not closed under contractions, but if we throw in contractions on top, can we get all gross substitute valuations? And it turns out that this is an open question looked at in multiple contexts, and then we went off in this rabbit hole, and now have a new paper with Edin, Georg on Zoom somewhere, yes, and Ben Smith, and upcoming soda, which means that the contractions of Rado is not equal to gross substitutes. And again, there were actually even stronger conjecture, or weaker, whichever way conjectures are there, that one can get all gross substitutes with even like a weaker set of operations, more restricted set.
Can you explain that again? You said Rado valuations are not closed.
Yes, so but if I look at all contractions of Rado valuations, like I take any valuation I can get from contracting a Rado, that will be closed under contraction. It will be closed under all like operations preserving cross substitutes you can come up with. And so yet you still cannot get all cross substitutes. Anyway, so like all known examples of cross substitutes are either from this class, or we don't know whether one could represent them from this class, except for some examples we came up with here. And so what I like about this class, I was very happy that like Yannick already figured that it's an interesting application for them. It has like very rich combinatorial structure, and one can use our favorite arguments there. So let me get back to the table now for a minute. So our main actually our main result with adding Juga and Juga is a very impressive 772 approximation, which guarantees fairness to the utmost way in the setting. So this was a stock this year. However, there was a paper by Jan Wondrak and Lee, the student Fanchang Lee, at Soda this year, which gave it has to do with E in some way, but it's a roughly 6.8 estimation algorithm. So they can estimate the optimal social welfare value within a way better factor for Rado valuations, as well as convex conic combinations of Rado valuations, which actually go out from gross substitutes. And what does this estimation algorithm mean? They basically managed to get this real stable machinery work and show that it has a bounded gap, but they were not able to round it in polynomial time. So it takes, like in expectation, it's exponential to find a good rounding. And what I found very fascinating, that like I wasn't quite aware of like this explicit notion of Rado valuations before, but actually they also, in a very different way, arrived at this as kind of a key class towards towards Nash social welfare. But we really, I guess, were better here is finding a name for this class. So we called it after Richard Rado, who first studied this independent matching problem in bipartite graphs. I'm happy to see that now this term is spreading. So anyway, so then, and I'll tell you why we thought that maybe this might extend to gross substitutes, but couldn't make all parts of the approach work. And like after we saw each other's papers and started looking at the other approach, and Wensheng and Jan won. So they actually extended like our approach, which I'll outline at a high level in the next minutes. Is they even got down below 400, and this time for general submodular valuations. And unless you start looking at what is there between sum-additive and sub-additive, this is pretty much the best as far as constant factors go, because so for sub-additive there is an order n approximation by Gar, Kulkarni, and Kulkarni, and this is actually that there's a hardness bound. So this is basically like really an factor n is what we have to lose if we venture from sum-additive to sub-additive.
Does this hardness also hold if you get this from an oracle? Because the 2 or 5 is only with demand oracles, right?
So this is with, I think this is with value oracles.
So this also, so the hardness is only for value oracles?
I think so, yes.
What about fractionally sub-additive?
Think there might already, the hardness might already be there, but I'm not sure. It's actually a paper by Barman and co-authors. I'll look up which is this hardness results. All right, so so much about the general setting, and now I try to give you some idea of what we are doing in our algorithm. So let me get back to the other board. And so the first step will be that we do want to start with this market relaxation, which we do know that it's not good. But so now I'm looking at NSW for Rado Valuations. So first, VI can be extended to a piecewise linear concave function on. So this is kind of what you would expect if you have seen matroid polytopes and matching polytopes. We would have these fractional assignment variables telling us that who participates in this matching to what extent, and so we can basically write with an LP, and we will look at xi's, which will be like this fractional assignment. So xij is the fraction of good j assigned to agent I. And why we were actually eyeing gross substitutes, that this fractional relaxation, so this is kind of the upper concave hull of the function, and this exists, or convex or whatever, and it exists if and only, and can be efficiently computed if the function is gross substitute. So you like, that seemed to be the limit of this relaxation starting point, which it turned out to be, they were too conservative in this, and I'll mention how Jan and Wenjang managed to get around this. But anyways, so what our like basic object is a mixed integer relaxation, which takes a subset of n goods, and the face of it, and now I'm gonna convert to, no, I stick with the original objective. So maximize the product of vi xi to the 1 over n, subject to the same assignment constraints, xij at most 1, x1 negative. And then I also want to require that xij is integer if j is one of these specially selected goods. So far I haven't done anything. I looked at fractional relaxation, and I chose a subset of variables, and I require those to be integers. And so this maximum I'll call opt h, the one I can get with respect to this h. And how am I going to compute this opt h? Well, it's, I'm sure, still be hard. And how do we pick h? So these are all very good questions, and I won't give full answers, but what the overall plan would be to carefully select an age, solve this problem approximately for that age, and then run that solution. And so what we can, this will be the lower bound guaranteeing, or we will have a proxy to this optimum, which will give our lower bound, and so you can see how all these factors multiply up to something very big, because actually the algorithm is very modular. So we go in 5 phases, and I just quickly write the names of this. So the first is select age. Phase 2, further relax the problem. Phase 3, approximately solve. So 4 is sparsify and round, and the 5th is recombine matchings. So what are these matchings we want to recombine? I just give you a few words about what happens in each. So first, how do I select my age? Starting point is that, well, surely I need to give everyone at least one good so that my objective is not 0. So what's the best way to give everyone a single good? So phase 1 will be find matching from agents to goods, maximizing the product of the V I sigma I. By this I mean the value on the set. So what's their value if that's the only good that they get? So here are the agents, here are the goods, and what we do is first just match them into this set. That gives us a set age, and those will be our set of some precious goods we put aside, and we will insist on a special treatment for that. Now, what would be a tempting thing at this point is, okay, so maybe let's, this is the basic allocation, this is what we give to people, now everyone got at least something positive, let's take it from here. Now, unfortunately, that's not gonna work. So why, just let me give you an example with 2 agents who have, well, there is this crown thing where they have utilities m and m plus epsilon. And then there is this other good where both of them have utility 1, and then this m plus epsilon person actually has like hundreds of other goods where he has utility 1, but these are completely worthless for the first agent. So as you see, this initial matching would give they use these cross edges, the m plus epsilon and 1. And now this first guy is stuck with getting utility just 1, whereas like the second agent is taking home the bank. So as you can see, this is not a smart thing to keep this matching forever. But what we it still does, looks at, singles out the items for which there is like a clash and everyone likes these items. So So those we somehow managed to identify with this matching age. And then, but as I said, we won't keep this matching around forever. And so in the remaining minutes, I'll try to give you a flavor of what we are doing here. So again, phase one was just pick this maximum matching. This we can clearly use our favorite bipartite assignment algorithm with the log of those weights. Phase two is we write sort of a mixed matching relaxation, which, as it happens, is not quite a relaxation. So we want to maximize the product of the sum of Vij plus Vi pi I, subject to the following constraints. So these Yij's are assignment variables, but just for these goods outside age. And then pi is a matching between the agents and our special set age. Okay, so why is this not a relaxation? In the optimal solution, it could be the case that actually the single guy is getting everything from the set age. So now we are taking n-1 goods away from him, which, or her, which might reduce their utility by a factor n. But the thing is that this can happen, okay, one guy can be really screwed, but then the others are not damaged by this operation, they're even getting extra stuff. So that's kind of one of the beauties of this product objective, that even if someone gets really on the receiving end, the others can compensate for that. So that's why this only loses constant factor by imposing a matching. And as you might have noticed, the objective also changed. I add up what you get from goods outside age and from what you get on your good on age. But the real thing would be just to look at this whole bundle of all goods. But luckily, well, this is what monotonicity and subadditivity guarantees. This is within a factor half of the real. And okay, so how do we solve? We still can't solve this. Amazing, right? And so this trick, we still cannot solve this problem. So what we first do is solve the Eisenberg-Gale just on G minus H. Like, ignore everything that is in age, ignore this initial matching we found, and then find.
László, can I ask you, why do we take the sum of Vi, Yj? Why not?
Yes, this is, thank you. There's something. Find matching pi between G and H that maximizes the objective for fixed y. So again, we found a fractional allocation that already gives you this starting utility. So now I'm not solving the same problem as originally, but I'm looking at, okay, what would be my increment in the utility if I got this one extra edge. So like it's kind of is separate, and it's a very crude separation of the two parts of the problem. First solve the continuous one, then solve the matching one. And so this is this gives a constant factor for mixed matching. For the mixed matching relaxation. And so then phase 3, so well, sparsify and round. So this is where we heavily use Rado. We look at the structure of this LP that describes the linear relaxation, and look at basic solutions and write auxiliary LPs and have fun with that kind of stuff. And after we sparsified, we actually just assign every good arbitrarily along the fractional edges. And this was, what happened? I missed the phase.
This is phase 4.
Yeah, this is phase 4. This was already phase 3. And phase 5, recombine this pi and initial sigma. So we started with this initial maximum weight matching, and amazingly we still need to, like, this rounding wouldn't do it by itself, but now we just look at these two matching side by side, and by like carefully looking at why that initial matching was optimal and why we changed it to another one, we can kind of backtrack on some of the alternating cycles and get the approximation ratio. So yeah, it's you know, seems like a bit of a roundabout struggling way. So like it's a bit disappointingly, it really doesn't match what I said, this elegance of the original additive algorithms. Yet it does work, and what like happened then I mentioned, and just I very briefly mentioned what Benjamin and Jan did, and then just my favorite open problem in this context, and then done. So what they do, Jan Ponjak is not someone who would be afraid of using a non-convex relaxation. So they use the multi-linear relaxation for submodular. And I was like, sure, but you cannot optimize that. And then one might point to this argument on the board. I mean, there is so much slack in every single step. Why is it solving the convex program optimally what we would care about? So you can, deploy a continuous greedy to solve approximately. And so that's the first key difference. You can go for submodular instead. Then you can still approximately solve this. What here we could solve exactly, but who cares? But otherwise, they really kept all these 5 stages of our algorithm. This is one change they made, and the other is where we went all the combinatorial, dirty, or hands with matroids. They actually just use a simple randomized rounding according to those yij's. It's that the algorithm itself is the simplest thing one can come up with, but to prove concentration that uses, probability beyond my mean. So anyways, I'm out of time. And then they tighten some screws here and there. So this goes down for submodular to 380. The time is up, 10 seconds. Anyway, so this is basically what I wanted to say, except if the chair gives me a permission for just one open question. It's very kind chair here.
We like open questions.
So Nash social welfare, I hope I convince you it's a nice problem, but one can also look at the asymmetric Nash social welfare, where it reflects to that society has some VIP people and those with that the means can push for more. So just a formalization of this, we have weights Wi, and then we want to maximize not the geometric mean, but the weighted geometric mean of the utilities. And so for this, actually our approach works, but just in a restricted setting. It gives some constant times W cube, where if the weights are chosen between 1 and this capital W. So it's kind of similar to what used to be for tree augmentation. You can get, here we can get constant factor just for these bounded weights case. But then for unbounded weights, even additive, even if I just have two different weights, but they can be far apart, even that's not known. And from our 5 stages, there is actually just one part where we use what the weights are, and everything else would carry over. And this one part is what I mentioned, is exactly the step I cleverly erased. So it was going from the first to the second relaxation, where we require that from this set age, everyone can get just one good. Like if there are some very high VIP people, and then the thing is, taking away all but one from such a person cannot be compensated by all the others. So that's the only step where our approach fails, that it's a kind of a very fundamental step which we just see no way getting around. But I think it's actually a very, very nice problem, and there might be interesting things down the line. So sorry for going over time, and thank you very much.